Hello, and today we're going to learn how to calculate standard cell potentials. Now this can be very useful, and I want to go through some of the common pitfalls that can occur. So let's say that we wanted to react copper solid and silver plus. What are we going to get? Well, one thing that you can use that can be really beneficial is looking at a table of standard reduction potentials. And this will kind of give you an idea of what kind of products you might be able to expect. So first, let's find copper solid. You see it right here, so we're going to be using this half reaction, and silver plus. And we can use this half reaction. So let's tackle the copper solid first. So throughout that half reaction, we have copper 2 plus 2 electrons, yielding copper solid with a standard reduction potential of positive 0.34 volts. Now, one of the things that we have to address is that we have copper solid in our reactants. And for the half reaction, it's in our products. So we need to change that around, and we can do that by flipping the reaction. So we can trade the products and the reactants. So when we do that, we're going to get copper solid yielding copper 2 plus 2 electrons. Now the other thing that changed is we went from a standard reduction potential to a standard oxidation potential. And the only real difference there is we need to change the sign. So we went from a positive 0.34 volts to a negative 0.34 volts. Now we want to tackle the silver plus. So for the silver plus, we are able to pull from our standard reduction potentials to have silver plus an electron yielding silver solid with a standard reduction potential of positive 0.8 volts. Now, one of the things that we need to address here is that our copper generates 2 electrons and the silver plus is only taking 1 electron. So in order to address that, we are going to need to multiply that equation by 2 so we can get 2 electrons. We don't have to do anything like flipping it because our silver is already in the reactant side, but we do need to multiply it by 2. So when we multiply it by 2, we're going to get 2 silver pluses plus 2 electrons yielding 2 silvers. Now one thing to note is that our standard reduction potential remains the same. Even though we multiplied it by 2, we do not need to change our standard reduction potential. And this is because when we're looking at volts, the unit of 1 volt is equal to joules per coulomb. So amount of energy per charge or per electron. So even though we're using 2 electrons, we're still getting the same amount of energy per electron. So that's why the voltage does not change. So now that we have our 2 reactions, we can combine all the reactants and all the products. So we'll combine all of our reactants and we're going to combine all of our products. And when we do that, we're going to get copper solid plus 2 silver pluses plus 2 electrons yielding copper 2 plus 2 electrons plus 2 silver solids. And another thing to note here is that we have 2 electrons in the reactant side and we have 2 electrons in the product side, so these will cancel out and we can simplify our reaction to simply read copper solid plus 2 silver pluses yielding copper 2 plus 2 silvers. Now we need to figure out what the standard cell potential is for this reaction. And that's going to be the summation of our oxidation potential and reduction potential. So we're going to be looking at the oxidation of copper solid and the reduction potential of 2 silver pluses. So when we combine those, we'll have negative 0.34 volts plus 0.80 volts. And we can figure out that is positive 0.46 volts. So since this is positive, it's going to be a spontaneous reaction, so it will occur. And we can use this process for calculating standard cell potentials for a whole host of different reactions. Anyway, I hope you found this useful, and definitely try to make sure that you watch out for the pitfall of multiplying a reaction by 2 does not change the potential. And if you ever have to flip a reaction, you want to change the sign of your potential. Anyway, I hope you enjoyed the video. I look forward to seeing you next time.